Hello, this is Alex from the National Weather Service in Norman, Oklahoma, and I'm happy that you all could join us for the Severe and Hazardous Weather panel for the National Weather Festival. Just to kind of introduce our panel speakers and also to kind of explain how things kind of came about, we decided to put out a poll to you guys, kind of a Dropbox to ask questions on severe and hazardous weather, anything that you possibly did, and we got lots of responses for us to answer for you guys. And we grabbed some people from the Weather Service in Norman and also some from the Storm Prediction Center, and we're here to answer your questions today. And so to kind of go around and introduce everybody from the Weather Service in Norman, we have, and if you guys want to wave whenever I say your name, we got Randy Bowers at the Weather Service in Norman, and we also have Vivek Mahali, Dr. Vivek Mahali, I should include that. And then from SBC, we have Andrew Lyons. We've got Evan Bentley. We've got Andrew Moore. And we've also got Jared Geyer. And so, no, we're all here to answer your questions. And so kind of to kick things off, we'll start off with kind of a roundtable. We'll all go through and answer this. First question is, what inspired you to be a meteorologist? And Randy, if you want to take it away.
All right, Alex. Well, I know a lot of people have maybe one single event that inspired them to be a meteorologist, and I really don't. I mean, I can name maybe top three events growing up in Tennessee that really piqued my interest and really solidified my decision to kind of go on and be a meteorologist. But as far as any particular event, I really can't say that there was a particular event that inspired me. So I've just always been fascinated with it, just watching the sky and the process of the way things come together, and whether it be wintertime, snow, sleet, freezing rain, or severe thunderstorms in the springtime. I've always just been very interested in that. But I guess I can just briefly mention the top three events that I can remember that really kind of that made me really realize that I definitely want to pursue meteorology. I will say that we had a big ice storm back in 1994 that impacted the area. We ended up with significant power outages for up to 2 weeks in Tennessee. There was another really big wind event that affected a very local area in my county back in 1995, in the May 18th, 1995. Really significant. We ended up with really high wind damage around kind of my section of where I'm from, my hometown. And then also, I would say probably a derecho event that occurred back in the early 90s as well that produced widespread wind damage.
All right, Vivek, take it away.
All right, thanks, Alex. So my interest in meteorology began by a somewhat classic story. I can actually pinpoint the date, April 25th, 1994, when I was in elementary school. That evening, a tornado went through my neighborhood in the South Dallas suburbs. After that event, at first, I was fearful of thunderstorms, but over time, that fear became an interest. And I think speaking to other meteorologists, that is a common story. I would always watch the weathercast on the news, and that summer I would draw weather maps from the Weather Channel. And over time, with the accumulation of events and being able to look at weather data online, my interest grew. I actually still remember looking at my first weather model in 8th grade, so I knew it was the right career for me.
Thanks, Vivek. How about you, Andrew?
Yeah, my story is kind of very similar to Randy. I don't have any explicit events that I really remember that got me interested in meteorology, but my grandfather on my mother's side was a weather observer and a pilot in World War II, and he had a lot of weather maps and a lot of aviation related stuff. And I grew up all around that and was kind of exposed to that from a very young age. And I just remember always being interested in meteorology and what's going on in the atmosphere. That really exploded in high school when I discovered places like the Storm Prediction Center and the National Weather Service, and was downloading maps, looking at data, all of that, and kind of knew that that was the place I wanted to be, and ended up here in Oklahoma.
Thanks, Andrew. How about you, Evan?
So I've always known I want to be a meteorologist ever since, really as young as I can remember. And it was interesting, a couple years ago, I went back and my mom had given me this, I'm the first child, so of course my mom did all these things, right? Like, so she had written a diary of like basically every week of like my life. And like sometime when I was between 2 and 3, she had this journal entry about how I was always staring up at the sky. And so really it just seems like there's something, genetically predispositioned in me that I've always just loved the weather. And, it's grown from there. There's been, every time there were significant weather events, I was giving, in kindergarten, I was given the weather report on the school bus every morning. And so, it's just kind of always been a part of me, always what I wanted to do. And now I'm living my dream, working my dream job.
Thanks, Evan. How about you, Andrew?
Yeah, so I guess my story is kind of a combination of Randy Bowers, Andrew Lyons, and Vivek's all kind of combined into one. So there wasn't a specific event that kind of turned me, towards weather. But I just remember being really afraid of tornadoes as a kid, and just living in Arkansas. We were no strangers to severe weather, especially tornadoes. And there are a few events that stick out in my mind that I just remember being terrified of it. And then kind of like Vivek said, as I grew older, that fear kind of turned into a curiosity, which turned into a passion. And since then, it's just continued to grow, and I found myself here.
Thanks, Andrew. And Jared, how about you?
Well, my starts, I grew up in rural Southeast Illinois, grew up on a farm, and I think that was a big influence into regarding my interest in weather, because growing up on a farm as a byproduct of farmers, weather is a daily conversation. It certainly was the case in our household, and I think just the discussions, the daily discussions, and sometimes sweating bullets in terms of whether we'd get rain and when we had drier conditions, that type of thing. I think that definitely left an impression on me, just the family's interest and keeping track of the weather, that type of thing. So that's probably the first thing. Otherwise, I grew up, I'm probably the oldest one of the bunch here, so I grew up, my weather interest was starting before really the internet was available and that type of thing. So availability of weather information is quite a bit different. For one thing, I just sit outside lots of times watching the clouds, listening to my no weather radio, and piecing forecast together, and trying to learn from the observations, just the little clues that I'd hear, and try to make what would be kind of primitive maps and that type of thing. And I even got to the point when we got my first computer, a Commodore 64, for some old school computer folks out there. I was able to initially start some programming and write my own weather forecasts, that type of thing. Various friends and family would indulge me and look at my little newspaper attempt at a publication in terms of a weather forecast. So those are some of the things that I can recall. I do have a formative type of event. It wasn't one of the more classic situations in where my home area was immediately impacted. Rather, it was on a trip. So as I mentioned, I grew up in rural southeast Illinois. My grandparents lived in South Texas, in Brownsville, Texas. And so once or twice a year, we'd make a trip down there to visit my family. And we were doing so right around Christmas time in 1982, I believe it was. We were driving through Arkansas. And I can remember being on the road. It was well after dark, and us having the radio on, and in short order of the course of the next, I don't know what it was, 10, 15 minutes or so, the emergency, I believe it was the emergency broadcast system at the time, basically every radio station that we would tune to was constant tornado warnings coming out. And as a 6-year-old, that definitely left a major impression on me. I can remember quietly being in the back seat, but scared to death, like what is going on? And it really left a mark on me how many cars were pulled off of the interstate that we were traveling on. It got to the point that we were the only car left on the interstate. And I even remember thinking as a 6-year-old, like, this is probably not a good sign. And unfortunately, we didn't know where we were, that type of thing. Well, it turns out we had some hail, but we got through it unscathed, and we stopped down the road after to kind of get a break from the heavy rain and some hail that we had experienced. And there were reports coming in of damage that we just generally knew was behind us, roughly where we'd been, that type of thing. And anyways, traveling back a week or so later, we could see some of the tornado damage from the interstate as we're going back through. And I'd never seen anything like that in terms of damage. And right away, knowing it was tornado, confirmed tornado damage in hindsight, that definitely left a mark on me in terms of just the power of tornadoes and what they can do. And certainly had a big connection to that, especially being after dark, not knowing what was going on. It was especially scary and left a mark on me as a 6-year-old.
Definitely. And so thanks guys for all the answers, and that's actually did a wonderful job segueing for me there. And so our first question, which will be answered by Andrew Moore here. Andrew, how do tornadoes form?
Yeah, so that's kind of the million-dollar question, isn't it? That a lot of us have been trying to figure out for a long time. So the good news is we generally know what to look for and like how they generally form. There are some nuances we're still trying to figure out, but if you want to break it down into the basics, there's kind of two things that you need. And the first one is you need some kind of rotation or swirly or just kind of some kind of swirl in the lower part of the atmosphere near the ground. And then you need some kind of rising motion right above that to stretch that swirl into a column of rotating air. That's basically how you form a tornado. And so if we think back to those two parts, let's just start with the rising motion. That part's kind of easy to get. All you need is an updraft from a thunderstorm. And so that happens all the time across the world. But getting the swirly motion right near the ground, that's kind of the tricky part. And that can happen a number of ways. And so I'll just use a really easy example. If we have an air mass or a boundary with wind going two opposite directions, that can tend to create swirlies along that boundary, such as like a stalled cold front or a sea breeze or something like that. Just some kind of stalled boundary. You can get low-level velocity or rotation near the ground, and if you get a thunderstorm developing right on top of that, it can stretch it, and that can stretch that column of air and tighten it up into a tornado. Getting it in a more caustic supercell thunderstorm, getting that little swirly near the ground is a little bit more complicated, and there's numerous theories out there on why that's happening. There's a lot of ideas that has to do with the rear flowing downdraft coming down and generating what we call vorticity near the ground. But this is something we're still looking into, and a lot of research is actually turning towards using high-resolution computer models to simulate tornadoes and to simulate how we can get that rotation near the ground. So we're actually getting really close by using computers, but we're still looking for we're using the computers, but we're still looking for those confirmed observations and field studies. So stay tuned because those details are still coming.
Thank you, Andrew. Moving on, this next one will be for Evan Bentley. Can you explain how downbursts form, and are they more prevalent in certain parts of the country?
So downbursts have a couple different forms that they can form in. And I guess to start at the beginning, when we're talking about a downburst, we're simply talking about air moving downward. So you have an updraft, as Andrew Moore was talking about, that are necessary for tornadic storms, but even just for any general thunderstorm. You have an updraft, which is the rising air that goes up into the atmosphere. Then it cools and condenses and it falls back down towards the ground. Well, in some cases, that air falls down very quickly. And so when it falls down rapidly, it hits the ground, has nowhere to go, and spreads out in all directions. So generally that can cause damaging winds. Now we can see it in many forms. Some days it's just what we call water loading. So on those days, it's just there's so much water up in it. Imagine taking a bucket and just dumping it out on the pavement. That's a lot of force it hits the pavement with. It jumps out in every direction. It hits people 15 feet away with water droplets, etc. That's a good way to think about water loading. It's just a heavy mass of water that just falls out of a cloud because the updraft can no longer hold it up. Then we have other more organized systems. The rear flank downdraft is one that happens in a supercell that Andrew Moore talked about that can be crucial for tornado development. But in the bigger forms, you hear about derechos, you hear about mesoscale convective systems. In those, they can be more organized. And this is a combination of evaporative cooling, which happens in the air. So when air cools, then that makes it actually fall more rapidly and can actually increase the downdraft strength as it comes down. And we can have many other forms that kind of organize these downdrafts. And so there's multiple ways that they can form, but the bottom line is when you have particularly strong downdraft is when you actually get the damaging winds. And that's generally what we see with actually the majority of severe thunderstorms are a result of damaging winds, which are always a result of some sort of downdraft, whether a more organized form, such as a MCS or derecho, or a less organized form where maybe a single cell thunderstorm is collapsing just under the weight of all the water.
Thanks, Evan. The next question is a bit of a long one, so we'll toss it to Andrew Lyons in that case. One of the more recent weather phenomena that we've really made the news recently are Firenadoes. So big question, how do these form? Where do they tend to be more prevalent? What's the difference between these and how, like, for example, you have Firenadoes, how do they compare to supercellular tornadoes? Are they viewable on radar? And really, are these kind of more frequent to occur in the future? Lots of questions. So go ahead and take it away, Andrew.
Yeah, so Firenadoes is a very interesting topic because it's something that's relatively new in the study of meteorology, but it's something that's been known about in the firefighter circles for many, many years. So the proper name for Firenado is actually fire whirl. And these form through several different processes across many different scales, but they're always driven in part by the heat of a fire. So what you need to make a fire whirl is a lot like what you need to make a tornado. So you just heard Andrew Moore talk about little swirlies near the ground and updrafts and air that's moving up. That is exactly what it takes to make a fire whirl. So you get the heat from the fire that makes the air very warm and buoyant. It wants to rise, and that brings air up with it. And if you have terrain, which near a wildfire in the mountains, a lot of times you're going to have very big hills, mountains, and valleys, and all this sort of stuff. That can cause local air currents to collide and produce spin near the ground. And that generates the spinning motion that gets sucked up into the fire column, and that results in the fire whirl. It's a lot like a dust devil. If you've ever seen a dry field or a baseball field and you see some air that's spinning in a circle picking up dust, that's the exact same process that's going on. But in fires, they're usually a lot more intense. So we don't actually know quite how prevalent these are. This is a relatively new area of research, and no one's really actually done anything in terms of counting how often they occur, what type of distribution they have, where they are most common. A lot of that can probably be traced to the wildfires out west, where you've got a lot of forested area and some very, very strong and powerful wildfires. But again, this is kind of a new area of science, so something that people are looking into right now. So kind of one difference between these and supercell tornadoes, the spin that is resultant or that results in the fire whirl actually developing usually comes from something that's much more local, something much smaller scale than what you have in a traditional thunderstorm tornado that you think about, like the Wizard of Oz. These are usually much smaller. So that can make prediction and figuring out how many are occurring much, much more difficult. Not to mention that everything is on fire. So I don't know if you really want to go charging in there to try and figure out where all these are surrounded by 500-foot flames. Another question I think was, are these viewable on radar? And the answer is it depends. So the term fire whirl is very broad. It encompasses these little tiny swirls, or sometimes these big burning columns that are hundreds of feet wide and miles tall. So the big ones, which I'm sure that's what most people are interested in, are the really big ones that we've seen recently. Those are absolutely viewable on radar. You can detect wildfires via National Weather Service radars. There's also several research radars, I believe, from several universities out west, San Jose State, and maybe San Diego State. They have radars that they point at wildfires to tell us how these fires are changing, and you can actually detect that. And you can detect the way the winds are changing in there and occasionally see those swirls and those fire whirls in there. So, and I think one more question, are these expected to become more frequent? The answer is we don't know. Like I said before, this is kind of a new area. We're not exactly 100% sure where all these are coming from and how often they occur. What we do know is that fires are becoming a little bit more frequent out west, and that is related to a lot of things in terms of fuel management, the climate, and some other stuff. So the long answer to that is we aren't sure, but generally speaking, if there are more fires, we would expect more fire whirls or firenadoes.
Thank you, Andrew. It's like I said, it's became very popular, big question back, especially with all the fires going on out west. So definitely a lot of area to explore with that. Next, we'll go over to Randy here. And question for you, is thundersnow rare? And if so, why?
Well, Alex, thundersnow, I would say it's pretty rare. I mean, if you think about all the snow events that you may have across the country, it's probably just a small fraction of those that have just enough instability to where you can have thunder that accompanies them. So it's really interesting. I think there are probably maybe two, I'm trying to think offhand, there are probably two mechanisms or or patterns that may support thunder snow the most. One may be lake effect snow that's common in the Great Lakes area. There's a lot of instability associated with that, so you can at times get thunder snow with that. And probably maybe one of the more common thunder snow events tend to occur with these very large, very organized systems that occur, especially across the central part of the United States. Within the northern or the northwest quadrant of those big mid-latitude systems that occur, sometimes you'll get just enough instability to where you end up with thunder snow with those. And these aren't going to manifest themselves on radar quite the same as your traditional thunderstorm. So it's not going to be maybe this red blob or this distinct thunderstorm cell that you see on radar. A lot of times it's not quite that simple. It's a little bit different. It's really the same process in a lot of ways, but it may look a little bit different on radar. So sometimes that instability that occurs that's just enough to create that charge separation where you have lightning and thunder with snow can occur sort of in a slant type. It's not a vertical system, and a lot of times it's more of a slant-wise type scenario. So what's really interesting too, just one thing I was thinking of as far as the thunder snow events that I've witnessed is it sounds a lot different. It's not the same as, say, your typical thunderstorm where the thunder may be prolonged, it may rumble for a while, it may be pretty loud. The acoustics tend to be different in these thunder snow events. A lot of times the snowflakes tend to sort of absorb the sound a little bit, so the thunder isn't quite as pronounced.
Well, thank you, Randy. And so the next question is a two-parter, which the fact that we have a forecast office and the Storm Prediction Center participating in this, it actually works out quite well. The first question is, when do you know to issue a watch? So your severe thunderstorm tornado watches. And for that, we'll shoot it over to Jared Geyer.
The Storm Prediction Center, otherwise known as SPC, we have the responsibility for nationwide issuances of severe thunderstorm watches and tornado watches. That's not only in Oklahoma or the southern Central Plains, that's actually nationwide. And we issue those watches in coordination with 120 plus National Weather Service offices around the country. For reference, nearly 500 watches have been issued this year to date through the first 9 months of 2020. And it varies greatly and depends on the activity level of each year, but we tend to have anywhere in the neighborhood of 450 to say 900 total watches each year. As far as watches go, in terms of their duration, they're typically in effect for a 4 to, let's say, 7 hour time frame, sometimes shorter, sometimes longer, but in general 4 to 7 hours is what we'll call it. As far as the size, they average around 20 to 25,000 square miles in size, but that can vary greatly based on the meteorological situation. For reference, that's a size roughly the state of, say, West Virginia, perhaps most of South Carolina, or roughly around the half of the state of Iowa. When all's said and done, on a national basis each year, roughly it breaks down to, of the total watches that are issued, roughly a third of those are tornado watches and about 2/3 are severe thunderstorm watches, but that again varies greatly by situation and by regional area. There's some parts of the country that are more tornado prone than others, etc. In general, the fundamental purpose of a watch is to provide advance notice of the possibility of severe weather. We're typically talking a couple of hours in advance. It doesn't mean that one should necessarily stop the routine activities, but it's a cue, a heads up that severe weather could be developing in your area over the next few hours. I should also note that not all severe weather, including warnings, is preceded by a watch. If it were, there would be some parts of the country that might have stretches, particularly say during the summer, in which watches might be issued on a near daily basis, really. But rather, watches are issued for more intense, more sustained, more organized, and persistent risk of severe weather. So in terms of the actual expectations when a watch is issued, severe thunderstorm watches are issued, we're expecting at least, say, a half dozen or more severe weather events, including large hail and damaging winds. We especially want to give advance notice and issue watches when there's the possibility of more significant severe weather episodes. That includes larger sizes of hail, say golf ball and larger, and stronger, more damaging wind gusts, 70 miles per hour or greater. It's those sort of events that we naturally want to give more of a heads up with a watch, typically giving people a couple hours lead time to that severe weather could occur in their area. That was severe thunderstorm watches. As far as tornado watches, we have the added element of tornadoes with that. Generally, for a tornado watch, we're expecting 2 or more tornadoes. That can be of any magnitude. 2 or more tornadoes is that baseline threshold as far as expectations in a tornado watch, or when the conditions are favorable for even stronger types of tornadoes, perhaps even on a singular basis, then a tornado watch would strongly be considered in those situations. As far as the actual ingredients, that's a whole webinar and seminar in itself. But in general, the way the atmosphere works and the way severe weather predictions work, it's kind of like any other recipe, baking a cake, for example. You have to have certain ingredients in place and certain conditions to take advantage of those ingredients. And when those conditions and ingredients are in place and exist, then watches may be issued to give that heads up and awareness that severe weather could occur.
Thank you, Jared. And I guess for the other half of it, when do you know when to issue a warning? Let's shoot that over to Vivek, and he'll give us the answer to that one. So take it away, Vivek.
All right, thank you, Alex. First of all, a severe thunderstorm by definition is 58 mile per hour winds or 1 inch or larger hail. And obviously a tornado warning is when we're concerned there's a potential for tornadoes. So, when issuing a severe thunderstorm or tornado warning, there are a few items that we look at. The primary tool that we utilize is weather radar to gain an understanding of the structure, intensity, and motion in a thunderstorm. But there are limitations in radar data, such as the effect of the Earth's curvature. So we have to use our knowledge and experience to fill in the gaps in radar data and try to anticipate the evolution of a thunderstorm. Now, radar data is not the only meteorological data we use. For example, the new GOES-R satellite can give us 1-minute updates. So that can provide us supplemental data. We also take into consideration the near storm environment. In other words, what's the thermodynamics and wind shear profile look like? What type of storms are favorable? Are there any boundaries in the area? Finally, if we have them, we take into account storm reports and the storm's history. That's why it's always important for people to give us storm reports. So if you've got a report, don't assume we know it, let us know. Ground truth is really useful. So we look at all the evidence and decide whether to issue a warning. But as you can see, there's no simple checklist. We consider many items at once.
Thank you, Vivek. One of the actually most asked questions for this panel, it actually involves kind of Tornado Alley and pretty much recent years and everything. And so we'll shoot this one back over to Randy. So tornado counts appear to be down across most of traditional Tornado Alley. Is Tornado Alley shifting? So go ahead and take it away, Randy.
All right, Alex. Yeah, that's kind of a difficult question to answer. I think there's been some research in it just a little bit that's kind of indicated that there has been some shift eastward, but it seems like there's multiple factors that are involved in that too. I know one researcher had found that maybe some of the ingredients that we look for tornadoes tend to be a little bit more frequent further east. There's other research that suggests that maybe we're seeing more of these smaller tornadoes, these QLCS tornadoes that occur within lines, that are being documented a little bit more. And since they tend to happen a little bit more frequently, maybe further east, maybe that's why the numbers in the east have increased a little bit. But there's really no solid answer as to why, from my knowledge, to why really we're seeing more of an emphasis further east. I think it's important to note, and when you think about it in general terms, is even if the numbers are a little bit different over the long term, we don't know if maybe there would be a switch backwards or forwards. You don't know if maybe that would change over time, but I think it's important to know that no matter what, we still get our fair share of tornadoes in the plains. And in fact, we still probably get more if you were to, it's just if you were to aggregate all the entire tornado count across the central United States compared to maybe the southeast. But it varies from year to year. And I think it's very important to kind of maybe focus on the fact that it only takes one tornado. So even if you're in an area that doesn't have a really high tornado climatology, you could certainly be hit by a tornado. But, whether the numbers go down slightly in the plains, it may happen for a decade or two and shift back, or it may be more of a long-term trend. Either way, it's one of those scenarios you have to be prepared. You have to know that certainly the entire area, regardless of a specific geographical area that may see a little bit of a trend, that the entire area still is under a threat, and it just takes one.
Thanks, Randy. So the next question that we have is another roundtable question. So we'll kind of go around to everybody and kind of input what they think, or actually in this case, their experience. What is the strangest, weirdest event that you've had to work? And so we'll go ahead, Randy. You seem to enjoy talking right now, so we'll go ahead and shoot it right back to you, Randy.
All right, sure. I think the strangest event that I've worked was when I was stationed in Amarillo, Texas, in the Panhandle. Well, there are numerous strange events there. I could probably have a whole list, and really everywhere that I've worked. But I would say this one really stuck out. It was a scenario to where we hadn't had tornadoes, really any tornadoes at all in the cool season whatsoever. So, I mean, the tornado climatology for the Texas Panhandle is very strongly biased towards the latter half of spring, especially the month of May. That's when most of the tornadoes occur in the Texas Panhandle. And I think this one event that I'm thinking of that I'll describe for you really shows how it's, it's important to always be aware that, certainly even though that spring may be when most tornadoes occur, that they can occur any time of year for most locations. And I think this event was one that really sort of showed that that's a possibility. So there had never been a tornado documented in the Texas Panhandle in the month of November until the November 16th, 2015 event. We had several significant tornadoes that occurred across the eastern Texas Panhandle. I happened to be the warning forecaster that night. Very hectic night as far as trying to, get the forecast together, understand what the environment was, how it was evolving. And we as forecasters, obviously we're in close coordination with the Storm Prediction Center as well. There's a lot of behind the scenes communication that goes between our colleagues there at the Storm Prediction Center and the local office. But it was fascinating because we looked at each other and we said, what would keep this event from not happening? These typically don't happen in November in the Texas Panhandle, but what would stop this from happening? And we couldn't think of anything. The ingredients were there. We had the shear, the instability. We had a forcing mechanism for thunderstorms to develop. And we knew if we did see thunderstorms to develop, we'd certainly see tornadoes. And in that case, we had some pretty large tornadoes. There's a lot of video online, some chasers that were out. A lot of this happened after dark. And, 2 EF3 tornadoes and a few other tornadoes that occurred as well. Some pretty significant tornadoes, and that being one of the bigger tornado outbreaks that we had in the Texas Panhandle for a long time, really, and probably to date for a couple decades, I would think, just how significant it was. So that really stood out to me as being one of the more interesting or strange events that I've worked.
Thanks, Randy. How about you, Vivek?
That's a tough question, Alex. There's some events that feel somewhat strange. For example, issuing severe thunderstorm warnings when temperatures are in the 40s. I've had to do that, or having severe thunderstorm watches and winter weather advisories at the same time. So I think events that maybe seem non-intuitive at first, but through over time, you do get used to it, and these events don't feel as strange, especially, I guess, living in Oklahoma, we get all these kind of wacky weather events because you kind of understand why they're happening. So over time, I guess I've become maybe numb to strange weather events because I'm like, oh, okay, we're seeing severe thunderstorms and hail in the 40s. That's happening again. No big deal, So that's sort of my answer.
Yeah, I gotta agree with you. Since working at the Norman office, yeah, you kind of get numb to some of the oddities there. Andrew Lyons, how about you? What have you got?
Yeah, so I've got two that are kind of my strangest ones so far. So I worked in several different offices over the last couple of years. I started off in Grand Junction, Colorado, which if people know their Colorado geography, that's on the western slope of the Rocky Mountains, and it's usually what people refer to as a high desert. So you don't tend to get a lot of rain there. And in the winter, a lot of times you get mostly snow. You don't end up with a lot of different mixed precipitation types, like say you would out here in Oklahoma and Arkansas, where you get freezing rain. So one strange event took place in January of 2017 while I was just beginning my forecast career out there. We had a system that was coming in overnight that we were projecting to produce quite a bit of snow. And, things were kind of progressing, and I was on the midnight shift and things were moving along, looked like it was on track. except until the precipitation started falling. I went outside at about 5 a.m. to do our balloon launch, and I remember seeing precipitation falling, but it wasn't quite hitting the ground. And I thought, that's strange. It should be, saturating all that. And a couple minutes later, then it started, and it was actually freezing rain, something that we had not ever recorded ever in the Grand Valley in Western Colorado, which had been settled since the early 1800s. No one had ever recorded freezing rain there. And it proceeded to freezing rain and freezing drizzle the entire day. We recorded over a ½ inch of ice at the office, and that was not in the forecast. And it brought the entire city to a standstill. They closed the interstate through there. All the schools were canceled and all that. And it was only the valley itself that actually saw the freezing rain. Everywhere else, it was all snow. So about a 20-mile wide by 40-mile long corridor of all freezing rain, and elsewhere surrounding all that was all snow. So my other interesting weather event took place in Cheyenne, Wyoming, which this is a bit more common, but still was a very eerie experience seeing it for the first time, which was raining ash from a wildfire. So we had a large fire, I believe it was the Beaver Creek fire in June of 2018. It had kind of burned all summer, and it was dropping smoke and ash, all that, into the city of Cheyenne. And you'd go outside on a day at noon, and it would look like it was sometime around 7 to 8 p.m. at dusk, just because all the smoke was blotting out the sun's rays in the sky. So those are probably my two most interesting experiences in terms of forecasting the weather. It definitely made things very challenging, and it humbles you quickly.
Definitely. Thank you, Andrew. Evan, what have you got?
So I have a story that is almost exactly the opposite of Andrew Lyon's story from when he was in Grand Junction. So I work out at the Portland, Oregon office for a couple of years, and out there they get freezing rain a lot. It happens a lot where cold air comes in through the Columbia River Gorge. It just comes in, kind of gets trapped in the train there, and then the system moves in, and for 6-12 hours you'll get a fair amount of freezing rain. And so one year we had like 6 or 7 freezing rain events while I was there in one winter. So it really wasn't that uncommon. But what was uncommon was snow. Generally, you could get snow down to 500 feet, 1,000 feet, but to get snow down to the valley floor in Portland rarely happened. Well, one day we knew that there was a colder event coming in. We actually were forecasting for it to be mostly like 34 and rain, which sounds like it's right on the edge, but 34 and rain happens probably a third of the winter in Portland. There's a lot of really cold rain there. But then in this event, right at the very end, we knew some cold air was coming in. We'd probably get a little bit of snow on the backside. Well, turns out the snow came in, except instead of coming in around 5 a.m., it came in around 9 p.m. and we had a lot of precip to go. So it started snowing, in the late evening. Next thing we know, we look outside, we've got 3 inches of snow, and our forecast was only calling for a couple inches of snow. And so we start playing catch up, and it just kept snowing the whole night. And the one thing out there is that we don't have great observations out over the Pacific, because we have the Pacific Ocean, which is big data void to our west. And as meteorologists, we really rely on observations a lot. And in this case, we didn't realize just how much upstream moisture was still heading our way. And so we ended up with I think the total for the event was like 13 inches of snow that we had, and all of it fell in like a 10 to 11 hour period. And so for an area that gets only a couple inches of snow a year, it was wild. That night, I didn't drive my car home. I walked to the train because I wasn't going to try and drive on that. And on my way home that night, I counted 140 abandoned cars on the side of the interstate. And it was surreal. It was, there were literally no cars on the road except for the ones abandoned on the side. And it was just perfectly quiet, just eerie, such a unique event. And so when events happen like that are so outside the norm for an area, it's such a surreal experience to be there for.
Sounds crazy, especially for Portland. Andrew, how about you?
Yeah, so I'm going to stick with the winter theme that's been going on here. So I used to work up in the Weather Forecast Office in Grand Forks, North Dakota, which is right on the eastern boundary with Minnesota. And so it's right smack dab in the North American continent. And so during the winter time, we had these really cold Arctic air masses that just come plunging down through North Dakota. And that can give us some crazy cold temperatures down to like -20, -30. And I believe it was this past winter, or maybe in 2018, I can't quite remember. but we just had this really cold Arctic outbreak that we knew was coming for days ahead of time. And it finally got there, and it just coincided with a bubble of high pressure that was also falling down out of Canada behind it. And with that high pressure, it created really strong pressure gradient winds. So we had really strong winds on top of really cold temperatures. And so that dropped the wind chill values down to like -50 to -60, and sometimes in some places -65. And I was lucky enough to work during the coldest part of that windy day. And we all took in the forecast office, we just took turns going outside and standing in it for a few minutes because it was just so uncommon to get that cold of wind chill values. And I'm from Arkansas and I went to school in Oklahoma, so I'd never experienced temperatures that cold before. So just standing out in the middle of a field, feeling -65 wind chill values was just insane to me. And that will always stick around for me.
I don't want to imagine -65-degree wind chills. All right, finish this off, Jared. What's been your weirdest or strangest event?
Well, Evan jogged my memory, and I can't decide between two, so I'll indulge and mention two quick. One, and I'll spare major SPC stories. You know, sometimes it seems like on a daily basis there are challenges or strange things that happen, but one of those, while at SPC, goes back a little more than 10 years ago now. Oklahomans might remember a Christmas Eve blizzard from 2009. And that event, particularly by Oklahoma standards and that type of thing, typical expectations. You know, obviously we're not the Northeast here or the Midwest that are much more you know, experienced in terms of winter weather, snow, etc. But a major blizzard, very strong winds on Christmas Eve. Maybe some areas, if I recall correctly, around a foot of snow. But the wind was the big story, along with the winds, the wind impacts in conjunction with the snow. And so getting into work was a challenge. It was what would normally be a 15-minute process was more like an hour plus, maybe an hour and a half. And then I will never forget what it looked like going home. Major Interstate 35 goes through central Oklahoma, including the Norman area. And basically I-35 was a parking lot the next morning. So I guess that would have been Christmas morning, I think. And it was a parking lot. I have pictures of it was a delivery truck that was just stuck in the middle of the interstate that had been plowed around, all kinds of cars and vehicles in the ditches, lots of cars stranded. It was just a very surreal sight, seeing all that, the aftermath of the blizzard, and how major it was, you know, people getting stuck and stranded, that type of thing. The other thing I'll mention, I'll go back to my local office days. I worked at office in central Nebraska, better part of, in general, this story goes back about 20 years ago. There was a local sort of outbreak of severe weather in September, not typically peak severe weather season in most locations, but in September of 2001, and wasn't a widespread severe weather day, but just in a very localized area, severe weather conditions became favorable, and as a really localized tornado event. We ended up having very long-lived supercell, including a tornado. Ultimately got a F3 rating on it. It was on the ground. I forget the details, but better part of an hour, if not an hour and a half. And the weird thing of why I bring up this story is I not only worked the event, I was on radar and the warning forecaster for that event, but I went out, and a couple of us went out to do the storm survey the next morning. And we're surveying the damage. We'd been there a while, and I don't know how we missed this, but as we were coming around a part of the house that we had not seen outside of it, and I wish I could show you a picture, so I'll just have to you know, follow along or envision it if you can, paint the mental picture. Basically, if you can imagine a larger size outdoor barbecue grill. This grill had a couple of spokes on the end of it for holding trays and that type of thing. So a larger type barbecue grill. This barbecue grill is almost like a magician's levitation trick. This barbecue grill had been picked up, turned on its side, and driven in by two spokes on the side into a tree. and it was driven deep enough into the tree to hold this very large, heavy grill without any other support underneath it. Like I say, kind of looked like a magician's sort of levitation type trick. And I just kind of did a double take when we saw that. And I've never seen anything like that in terms of, some of the fluky type of things that can happen with tornadoes. But that barbecue grill had been completely driven into the tree. The tree was fully supporting it, the weight of this large grill. And, it seemed like a 1 in a million or billion type shot. So it's hard to do it justice without a picture, but that's definitely one of the weirdest things I've ever seen related to a tornado or anything for that matter.
That's crazy. Thank you everybody for your answers on that one. For the next question, we'll shoot it back to Vivek. Vivek, what are the different types of radars that we use?
Well, Alex, I guess there's actually, two radars that we primarily use. The primary one is actually the WSR-88Ds, which stand for Weather Surveillance Radar 1988 Doppler. These were deployed in the early to mid 1990s, and over the years they have had several upgrades, including higher resolution data, dual pol, and the ability for faster low-level updates. The other type of radar we utilize are TDWRs, which are Terminal Doppler Weather Radars. These are located near major airports. We have one in central Oklahoma. Now, these have a shorter range than the WSR-88Ds and are more susceptible to a loss of signal. We call that attenuation, which occurs as the radar beam travels through heavy rainfall and hail, but they do have faster low-level updates and higher resolution data than the 88Ds. So we use them to supplement the 88D data. Now, some other forecast offices have access to other radars, such as university managed radars, but overall, those are the two primary radars that we use.
Thanks, Vivek. All right, so the next question will be for Andrew Lyons. How has our ability to predict supercells and long track tornadoes improved over the past 5 to 10 years?
Yeah, great question. Supercells and tornadoes are a difficult forecast problem. Like we've talked about before, they depend on a lot of small scale factors, and observations, like Evan has mentioned too, play a huge role in forecasting. So the things that we've done over the last couple of years that have really improved that have mainly been related to changes in radar, changes in research, and also just general forecasting knowledge, which has improved significantly. And that is owed a lot to the long-term veteran forecasters like Jared, who have been there for a long time and provided a lot of insight into how these storms happen and how we can improve the forecast around them. So I want to kind of dive into each topic a little bit. So Vivek just mentioned the radars and the changes in the radars. Those have become extremely important in terms of forecasting tornadoes and supercells. So once we actually get a storm going on, now we have the ability to use the Doppler velocities and things like that to look inside the storm and see how the winds are changing, how tall the storm is, how strong the storm is. And that is played probably the biggest role in terms of the short-term forecasting that we've been able to do. Once you have a storm and we know that it's spinning, we're pretty much able to always say, oh, this could be a potential problem here, in the next couple of hours. And we always watch those ones very carefully. In terms of the other research and things like that, there have been many field projects that have gone on the last couple of years. One of the most famous ones is called Vortex, or the Verification of Rotation in Tornadoes and Supercells Experiment, I believe. I probably butchered the acronym, but basically it's just a bunch of people that have driven out near storms and tornadoes, and they've taken all these mobile Doppler radars and these mobile systems and said, let's bring the sensors to the tornado instead of waiting for the tornado to come near the sensors. And that's what they've done, is they've mapped the wind fields around these storms, and they've also dropped weather balloons and things like that. And that helps us understand the environment that leads to these tornadoes. And with that data, we've been able to go back and put different things and different ideas into weather models and turn those weather models into more high resolution, better focused on the physics, and that provides a better answer in terms of the long term of, hey, how often are we going to see tornadoes? Where are they going to form most likely? And what days are they going to be most likely, and that sort of thing. So that's kind of what has changed in the last couple of years. We have a lot of future things that are also going to change too. things like artificial intelligence, machine learning, and other research projects focused on really, really small scale modeling. So the big thing with tornadoes is that they're such a small scale compared to what's going on in the rest of the atmosphere that they're very difficult to model with computers because it takes up so much data and so much time. But that's changing here in the next couple of years, and in the future, as we get into better computers and using all the old data that we've had before and machine learning, we can kind of start to pull data out that we haven't been able to before. So that's a very exciting category of supercell and tornado research that's going on and going to be going on here in the next couple of years. But just to kind of wrap up, we've definitely gotten a lot better. The warning lead times, while they haven't increased dramatically in the last couple of years, when we first started doing them, they were about 3 minutes. Now here in 2020, it's over 15 minutes of lead time on average, which is fantastic. So we've definitely gotten better, and the sky's the limit for us, pardon the pun, but it really is. And we are going to continue to get better at this too.
Thank you, Andrew. And actually talking about artificial intelligence segues perfectly to our next question for Randy here. How do you see automation impacting the job of the forecaster for the future?
Well, Alex, that's a good question. That's something that we put some thought into. I know we've had some good discussions in operations about that, but I think where we're at with it now, there's been some really exciting tools that have come out from some of the folks that have been involved in that at SIMS. I know with Prob Severe and with the storm scale modeling from the folks at NSSL. These are just a few that I'm mentioning now, but the Prob Severe is really interesting because it is one of our first ventures into sort of this machine learning and artificial intelligence realm. And so what it does is it just makes our job a little bit more efficient. Instead of us having to look at all these different variables and keep track of all these different things, it can sort of provide this statistically calibrated guidance that is a good first start for us. Then we can just focus on what the human is really good at focusing in on, and that's base data analysis. And by that, what I mean is kind of building on what Vivek was talking about with the various radars, is we can look not just at the half-degree radar or the lowest elevation angle, which I know most people are used to seeing that on television screen. Typically, that's what they'll display. But we're looking at the full volumetric of the storm. We're able to look at the upper parts of the storm all the way down through the lower parts of the storm. So we can pick out some of these features like the things like three-body scatter spikes, which is just a different way the beam may behave when there's a lot of hail in a storm. Boundawick echo regions, which are these features that indicate you get a really strong updraft. These are the things that are really important for us to take this guidance. It's already good and it's getting better. And as Andrew said, the sky's the limit. So who knows where this will go? But then in the current state, what we can do is we can make that even better. We can add the human analysis part of that, the conceptual models, to make the best decision possible. And then in the future, who knows where this is going? It's just exciting to see where we're at. It's anybody's guess as to when the forecaster will be more hands-off and not do as much. It may be another decade, it may be a little less, a little bit more. Those are questions probably that I think hopefully over time we'll get a handle on. But I think with time, we provide our analysis that we can add to it, but also I think just us being able to kind of take that information, since we have the base knowledge, and make it relevant in the way we communicate it. That's another big part of our job now. So really don't have an answer to the question except for it's exciting what's coming down the pike, and I'm excited to see how the forecaster can interface with that.
Thanks, Randy. All right, switching gears a little bit. Next question will be for Jared Geyer. So there appears to be an inverse correlation between the number of hurricanes and the severe tornado seasons. And the general question that's kind of being asked here is, how does El Nino and La Nina impact tornado seasons?
Okay, great. First of all, great question. I appreciate that question. Let's start with a little bit of background. First, what is El Nino, La Nina? Those are basically phases, part of the El Nino Southern Oscillation, otherwise known as ENSO. That's ENSO. And so ENSO is a natural climate cycle in which there's a periodic cooling and warming of different parts of the tropical Pacific Ocean. And believe it or not, those sort of oscillations can have influences on the weather patterns across the world, including here in the United States. So La Nina is the cool phase of the ENSO cycle, this pattern. And we are in La Nina conditions right now as of the last couple of months, I believe, late summer, early fall. And expectations are for that these La Nina conditions will continue through the winter in all likelihood. La Nina winters in general tend to favor warmer, drier conditions across the southern tier of the U.S., especially in the southern plains, where it's not uncommon to see drought and wildfire, favorable sort of conditions in some areas. However, where the east of where those warmer, drier conditions set up, it seems oftentimes that there's a heightened severe weather likelihood during La Nina. That's generally talking about parts of the southern plains, the eastern parts, the lower parts of the plains, if you will, the Ozarks, the mid-south region, the lower middle Mississippi River Valley. So in general, that's in terms of states, general areas that I'm describing there, roughly say eastern parts of Oklahoma, eastern parts of Texas, into Missouri, Arkansas, Louisiana, eastward into Mississippi, western parts of Kentucky and Tennessee, to kind of narrow it down there to kind of paint a picture of where risk can sometimes be heightened. There have been some notable regional tornado outbreaks during the fall and winter when La Nina conditions are present. So that's certainly something that we'll be watching for going forward. One thing to keep in mind is that there's a lot of factors that go into favorable environments for severe weather, including tornadoes and tornado outbreaks. La Nina and El Nino, for that matter, those are just background influences. So we can't pin individual events on La Nina or El Nino. However, favorable severe weather ingredients do tend to more commonly come together in the case of La Nina, such as I previously described. Now, that was La Nina, and that's the phase that we're in and likely to continue through the winter. In contrast to that, stronger El Nino conditions have generally been associated with below average severe weather. That's particularly the case for parts of the southern plains into the deep south. One possible exception to that is parts of Florida, southern Georgia during the winter time. Sometimes they'll, with an enhanced jet stream and more southern storm track, very far south areas may have a heightened severe weather potential during El Nino, but otherwise it tends to be below average for other parts of the plains in the southeast.
Thank you, Jared. Next, we'll go over to Evan. And what would you say causes highly unstable environments to sometimes not produce storms?
So the ingredients for a thunderstorm, we always talk about moisture, instability, and a source of lift. And so if we're talking about an unstable environment, obviously it's unstable. In general, we're talking that it has moisture also, because we're really talking about these hot and humid environments. The day when you're like, wow, it really feels like, a thunderstorm day, it really feels like it could rain today, but it doesn't a lot of those days. So what are the keys behind that? Well, it comes down to a few reasons why. There are different forcing mechanisms, and I won't get into details of all of them, but some of them are, you'll hear us talk about mid-level short waves and things like that that can cause just some general rising motion. There's dry lines, cold fronts, individual boundaries that can cause more rapid rising motion and can cause thunderstorms to form, etc. But really what that forcing is there and needs to occur is to overcome what's called a capping inversion. So you might hear it called a temperature inversion or a cap. And a lot of these days, when the cap breaks, that's when the thunderstorms are going to hit. So what are we talking about? Well, there's a lot of really hot air that forms over the higher terrain of the desert Southwest. So there we're talking terrain that's between 3,000 and 6,000 feet that warms up well into the 90s and hundreds a lot of the days, in the spring and early summer. And that air, generally the air across the U.S. is going from west to east. So that air comes across the plains at 3,000 to 6,000 feet, but here we are down at 1,000 feet to 1,500 feet across the plains. So that hot air is coming in above us. And so at the surface, we've got cooler air. So we need to warm either for the surface to be able to overcome the kind of lid that's put on the atmosphere, or we need one of these forcing mechanisms to help us kind of bust through that lid. But that lid is also really important for having severe weather, because if there was no lid on the atmosphere, we would just, as soon as the temperature got warm enough, we would immediately form storms or form showers, really is all they would be at that point, and we would get a precip out of it, and then it would be done. It's kind of thinking about a stream. You've got a stream that's just constantly flowing. It's got a little bit of water going through it, and it's fine. But then you throw a dam in it. And if you poke a little hole in that dam after you've made that stream, you've got, boom, powerful water going through it. And that's what happens with the capping inversion. You've got a capping inversion where everything's just kind of calm, and all of a sudden one hole breaks in that capping inversion, you get a giant thunderstorm that forms really rapidly. And so kind of holding back and letting temperatures get hotter and more unstable before you get storms to form is one of the reasons why we get such strong storms, especially here in the plains where we have the capping inversion to kind of hold things back until it gets really unstable. It causes the storms to be more intense.
That was a great explanation there, Evan. Next, we'll go over to Andrew Moore. Are waterspouts associated with a mesocyclone, and does the EF scale also pertain to waterspouts?
Yeah, so that's a really good question, and the answer to both questions is yes and no. So I'll start with the first one on whether waterspouts can be associated with mesocyclones. The answer is absolutely yes. We've seen this, several times where you have supercell thunderstorms over the ocean, especially over the Gulf of Mexico, where it's a normal supercell, it just happens to be over water. And they're close enough to shore that our radars can pick them up, and we can see that they have incredibly strong rotation. And sometimes we even get reports from boats or maybe people on the shore who can see out far enough of a tornado or a waterspout associated with the supercell. And so that, if that was on shore, we would consider that to be a really typical supercell thunderstorm associated with a mesocyclone, or the tornado would be associated with a mesocyclone. But waterspouts can also form just with a confluent boundary. So earlier I mentioned how you can sometimes get confluence along a stationary boundary, and if you get thunderstorms initiating along that boundary, it can stretch that, little swirly at the ground and form a waterspout. So you can get waterspouts in both ways. Now, if you're going to think about it in terms of an EF rating, that's where it gets kind of tricky, because the EF scale is solely based on damage. And if the tornado or the waterspout's over the open ocean, it's not hitting anything unless someone gets really lucky and is having a bad day and sails their boat into it. Like I said, there's no damage, so it's really hard to rate them. And so until they move onshore and actually begin to cause damage, we really have a hard time knowing exactly how strong that is.
Thank you, Andrew. And for one final question, which I did warn everybody before this before this meeting that I was going to ask this question. So, please rank the following Hollywood weather movies from most to least scientifically sound: Twister, The Day After Tomorrow, Into the Storm, Sharknado, Sharknado 2, the second one, Sharknado 3, Oh Hell No, Sharknado 4, or sorry, not Sharknado 4, Sharknado The Fourth Awakens, Sharknado 5, Global Swarming, and the last Sharknado, It's About Time. Anybody want to take a crack at it? You can go ahead and unmute yourself, because I get a feeling that this is going to go nowhere. Nope.
Alex, am I a bad meteorologist for not having watching Sharknado?
I will be.
will
Have
second
any of you
that
guys watched
question.
any? Have any of you guys watched any of the Sharknados?
No.
I've seen the first three,
First one,
sadly.
first three. You're braver than most. The only person I think I know that has seen all the Sharknados is probably Alex Lamers over at WPC, if you guys know him. So, but unfortunately, that's a call for another time. So, I wanted to thank all of our panelists for participating here today. Some great questions that were given to us and some great answers that went along with it. I hope everybody enjoys the this panel and also enjoys the rest of the Weather Festival. Hopefully we get to do this again sometime in the future. And until then, I hope everybody has a great evening.